Okay. It's great. It's great for me also.
Thank you, sir. Thank you, sir. So, uh, ladies and gentlemen, we are on the 100th day or 100th program of our mass awareness campaign on electrical safety. And today, the 100th program is by Professor Dr. R Nagabhushana on the subject of lightning protection. One moment, I just wanted to check whether I'm recording the. Yes, I'm recording. Yeah. So today we are going to discuss about the three subjects. In the previous 4 days, 4 sessions, we had discussed about the basics of lightning, then how to protect human beings, and then the third day, how to protect buildings, and the ideas behind the protection angle, rolling sphere, and so on. Today we are going to discuss about some illusory methods of protection, then possible laboratory testing and limitations of those the testings, and then lightning power transmission system, basic insulation coordination. These are the subjects of today's webinar. So today is the last day of our 4 days program. Probably we can have a longer question answer session because last time we could not participate all the questions or ask all the questions. But before starting, I would like to make a small presentation on what is this Vidyut Surakshit Bharat Abhiyan. So this campaign called as Vidyut Surakshit Bharat Abhiyan. This is started during last year. Every year, the Power Ministry had made 26th of June, 1 week as the Electrical Safety Week for the nation. So we started our activity on last year during this Electrical Safety Week. The program is uh, the name came into as a WhatsApp group we started, and Dr. PK Mr. Sri PK Patnaik from Odisha, he suggested this name, and then suddenly things started moving. Now the program is organized by CISA and LARC, Center for Innovation in Science and Social Action. It's an NGO based out of Trivandrum. CISA is into various science-related activities. And we have a LARC Center, Lightning Awareness and Research Center, which we started during 2004 or 2005. Since then, Dr. Nagabhushana was supporting us in several ways. During the first initial years, Dr. Nagabhushana was always traveling to Kerala, and we were traveling to different cities and making a lot of awareness classes on lightning. So CISA is an REC, Regional Center for Excellence, accredited, acknowledged by the United Nations University for Sustainable Development Goals, for supporting the Sustainable Development Goals of the United Nations. So we have selected this particular subject of electrical safety because at the moment, all of you knows very well that the situation of electrical safety is not good in our nation. A lot of accidents are happening and a lot of people are dying. Also, the some of the reports which we got from the seminars or the study reports, it says the electrical safety situation. For example, this the what you are seeing in the screen is a report of submitted by Mr. Takashi Honda from Japan. They made a presentation during the 12th April 2016, and according to them, about 723 people. Of course, these figures are from the National Crime Records Bureau. Annually, about 12,000 or so people are getting electrocuted. This means about 723 people per 100 million population per year. This is the number of people getting electrocuted, not fire. So additionally, in addition, a lot of fire accidents are also happening. And finally, they made a safety score, and India got the lowest score out of G20 nations. So our situation is actually not very much encouraging. So we selected some of the subjects for the campaign. Basically, 7 subjects were taken. Out of that, more focus was given to the subject of earthing, because the engineers in India think that earthing means something in the soil, and they start doing research on putting a pipe in pipe, plate in pipe, some chemicals, and so on. So actual subject of earthing has very little to do with the earth electrode in soil, but earthing is totally, a different subject. Then we have selected the subjects such as basic design criteria of low voltage electrical installation, inspection testing, solar PV, lightning protection, and surge protection. Please note that the focus of the program is only to protect people within the building, not on the distribution or on the transmission and distribution areas. These are all low voltage system, because in the transmission system or distribution, only experts, skilled people are going to work, whereas in the low voltage, all normal people are there. We have a team of technical members supporting the program, starting with Mr. Apau, Mr. James Kuti, Mr. Vinay Nagdio. All the three are retired from the electrical inspectorate of the state government. Then we have Mr. Patnaik from OPTCL, Mr. Devdas Goswami from BIS, then Mr. Mittal and Mr. Srinivas. They are electrical consultants, and I am working as a coordinator. Under Vidyut Suraksha, we also have the LARC, or the program is organized by LARC, Lightning Awareness and Research Center. Under LARC, we have a big team of scientists, those who are supporting, starting from Dr. Nagabhushana, also Mr. James Kuti Thomas, Professor Pradeep Kumar Dikshit. He is the professor and head of the Department of Electrical and Electronics Engineering in MS Ramaiah Institute of Technology. We have Dr. Anirban Guha from Tripura University. Also, we have a list of international experts, those who are supporting our program. We conducted one exclusive program on the early streamer emission protection, what exactly it is, and how the French standard is explaining about ESE. Last year, July, we conducted it, and this was we got a very good circulation of these programs. Now we have a blog in our website. You have to select, you have to go to vidyutsuraksha.com. There is a blog, and all the programs which we are doing, majority of the programs are included in this blog. Now, for example, the most awaited webinar, lightning protection, in that blog, you will be able to see the entire proceedings of these 4 programs, including the videos, including the subjects. So I request you to go through the videos even if you miss it. The program is supported by various organizations, the Bureau of Indian Standards, the Central Electricity Authority, and Railways. All of them participated, and today is the 100th program. Totally, we covered. Totally, there were about 25,000 participation for this program. By this, I would like to stop the presentation. Over to you, Dr. Nagabhushana, sir.
Thank you very much, Mr. Gopakumar. It's really very heartening to see that you have taken a very leading role in this very critical area of lighting production and electrical faults and injuries, etc. It's a very major area. It's a major area. It's very difficult for any one individual to take such a leading step, but it is really very highly appreciable that you have done it, along with, of course, many stalwarts who have been with you to support your effort. Now, I think it has been a very great privilege for me to be associated with this from quite a long time. Only thing is, if I can spread the knowledge a little more to whatever I know, I cannot claim at all that I know a good percentage of the knowledge also, but whatever I know, I'll be willing to share with anybody who is interested in this area. Anytime. That will be most welcome. Therefore, we go to the today's topic. Of course, I must really welcome all the participants. That I really miss saying that. I'm welcoming all the participants. I hope they'll be able to enjoy their participation in this, and also probably get some new knowledge. Particularly today, we are going to talk about some very, what should I say, false claims of lighting protection by some extremely simple or extremely complex devices. Both are there. We will see as we go further. Now, as Dr. Gopakumar said, in the first webinar, we discussed very briefly about the physics of uh, atmospheric electricity, with particular reference to lightning, the global capacitor, the transient luminous events and lightning, role of lightning and the characteristics, lightning flash density, which is highly probabilistic in nature, isochronic level, which defines the lightning incidence in a given area. Of course, all the things are probabilistic, which we should not forget at all. Isochronic level being the number of strokes per kilometer square per year, that unit area per year, is a very important parameter. Then we discuss the hazards due to lighting for humans. And of course, human property is the fire hazards, the hazards to humans by streamers, by direct strokes, streamers starting from the head typically, direct strokes, contact with the objects struck, and proximity of the objects struck, mainly by means of side flashes, ground currents, conductor currents, and then most importantly, how to avoid these hazards. As was mentioned earlier, the number of fatalities in India is the highest in lightning related area. Of course, the property damage is extensive in other areas like tsunamis, hurricanes, things like that. But the threat to life is the highest in lightning related events. Avoidance of the hazards, then of course the typical injuries. I did show a number of photographs to show the worst possible types of injuries and also a list of various injuries recorded. And survivors also have given a lot of data in this area. And then in the previous webinar, there's the third one, we discussed the basic principles of production of tall buildings, which was by means of air terminals using geometric method or the electrogeometric method, which is also known as the rolling sphere technique, and of course the mesh being inevitably necessary in most of the broad area buildings. And then the down conducts and earth systems, as I mentioned a little earlier, we discussed the basic principles. If you want to consider all the details, how to do it, what are the difficulties, how to encounter or solve the very difficult situations, one has to go to the standards where very, very detailed information is available. I have given the reference to various standards, IEC 62305, parts 1 to 4. Particularly 1, 2, 3 parts are very, very important for these issues. Now, today, we'll be discussing mainly unfounded and somewhat illusory techniques. Whether they will work or not, we'll be examining in some detail, so that people have been made to believe that it works very well, but it has been found that it doesn't work at all, both by means of technical logic. It's not simply logic, it's technical based logic and then based experiments. Then the very tall claims of ESC systems, very, very tall claims of ESC system, we'll be examining in some detail. And finally, we'll be discussing something about the lightning laboratories availability in India. Luckily, I have been able to contribute significantly to development of various laboratories within India. It's a fairly good number. And finally, of course, the so-called lightning test facility, which was set up by me and my colleagues, which was financially aided by the Aeronautical Development Agency, primarily for testing and verifying the lightning performance of light combat aircraft and its component systems. Fighter aircrafts cannot wait for the thunder weather to clear or whatever it is, whatever happens at that time, it must be able to face it without any problem. The risk is both to the pilot's life, which is very, very precious, particularly during wartime. Even one pilot can mean a lot. And then, of course, the aircraft also is a very important element. If you lose one aircraft during a wartime, it becomes very serious. Therefore, fighter aircrafts are far more important from the point of lightning production. So the lightning test facility was set up with the main purpose of testing LCA and its components for its performance under various strict, rather most severe lightning conditions that's probable. I will discuss that in some detail. That will give you an idea of whether it's possible to simulate lightning effectively in a laboratory, what tests can be done, like that. We'll be discussing that in some detail. Now, we'll start off with the so-called claim of a large area protection by using a very simple technique, a tall pole, a single tall pole with a cycle rim, with the metallic part of the cycle rim at the top. No tire there, of course, only the metallic rim is there. It has been proposed, but who really proposed it? But it has been put to use somewhat widely. I understand that such a single tall pole, about 40 feet in height, with a cycle rim on top, can provide protection from lightning over large areas. That means sometimes it is stated that a whole village can be protected. Apparently, it has been also installed at many places, and it has been claimed that in those areas, lightning incidence has come down. It's the most surprising claim, because does it mean that these tall poles have really shooed away lightning? Don't come here, something like this. Is it a possibility? Then why does not a transmission line tower shoo off these lightnings? Why should it occur to transmission lines itself? It's a big issue there. Therefore, we'll discuss this technical basis for these things a little as we go further. This figure 1 shows 2 photographs of these tall poles. In the first one, of course, I think they must be sort of an inaugural function. The second one also probably is an inaugural function only. The two are slightly different. The way the cycle rim is mounted on top is slightly different between the two. Now, on the face of it, it looks as though there is no down conductor. That means how does it protect? It's a very serious issue. We'll discuss the technical aspects as we go further. Now, some aspects of relevance to this tall poles is discussed in webinar 2 in some considerable detail. Now, in summary, these tall poles present a very highly dangerous contact potentials. In fact, in the second webinar, we estimated what is also even for a mean current. That means what's the current with 50% probability of occurrence. In fact, it's about 40 kA, 35 to 40 kA. We consider 40 kA. And if this passes through a tower, metallic tower, not a wooden tower, it can create momentarily 10 million volts momentarily. And inductive voltage of the drop, is of the order of 100 kV for a rate of change of current, 10 to the power of 11 amperes per second. Lightning is a transient current. There's a high rate of rise. In fact, the currents can vary with time. There can be several such voltage pulses. 10 to the power of 11 amperes per second is on the higher level, but it cannot be ruled out when it's in the public space, when the so-called tall pole with cycle rim on top is in the public place. How can we avoid lightning occurring? Therefore, we have considered 10 to the power of 11 amperes per second partly on the higher side of occurrence. Both the contact potentials and then this inductive voltage of 100 kV are very dangerous. The magnitudes itself will tell you they are extremely dangerous. Now, if you consider skin effect resistance of 1 ohm, which is not very high, normally I must emphasize here that even if you think of a metallic pole, the resistance of the pole from the top to bottom may be of the order of a few milliohms. That's the DC resistance. But with the transient current, the resistance depends upon the frequency. This is known as the skin effect. And therefore, under such lightning transient excitations, you have to consider the skin effect resistance and not the DC resistance. The other aspect is the surge impedance. Surge impedance is what's offered by the inductance of the pole and the capacitance of the pole with respect to ground. This is the surge impedance. It will be very difficult for me to go in detail into this concept of surge impedance, but let me, in summary, tell you that a tower of a single pole can be expected to have a surge impedance of the order of 150 ohms. So even if it's a 40 kiloampere stroke occurs, the potential developed due to the surge impedance drop is of the order of 600 kilovolts or even more. Obviously, these volts are not small. They are extremely dangerous. If anybody is in contact, they are likely to get a very high shock. The shock, please remember, is due to the current entering, current being forced by these high voltages. If the voltages are not high, it will not be able to drive the currents. That's the important point. These voltages are very high, they'll be able to drive the current. So part of the lightning current will throw the person or the animal in contact with the tall object. So this single tall pole, being a tall pole, is attractive to lightning. Nobody can deny that. Nobody can deny that. Whoever is proposed it also cannot deny it. Any tall object is more attractive to lightning stroke attachment. Therefore, contact can be very dangerous to this. Animals can be in contact. Humans, for example, we have seen that some of these poles have been erected in the areas of school buildings or hospitals. If the students, young students, or the patients from the hospitals are walking around for any reason, whatever, I must mention one point here. Lightning can occur in dry weather also. People would have observed it. So people may argue, if it's rainy, why should they stay near a tall pole? Forget the rainy weather. Since lightning can occur during dry weather also, it can be dangerous. At that time, it can be very dangerous. People can be moving around. They are subject to these very serious contact potentials. And then, once the lightning strikes the tower, the current flows through the ground. I have to mention again emphatically that soil is not having zero resistance. It has got a very finite resistivity, typically ranging from 1 to 10 ohm meters for very, very good soil from our point of view, alluvial clay and things like that. Very low, down to 10 ohms meter, ohm per meter, ohm meter, not ohm per meter, it's ohm meter. A normal soil can be thought of as having anywhere from 40-50 ohms to 100 ohms meter. Very rocky soil, sandy oil can have tens of thousands of ohm meters. We have assumed a value of about 50 ohms and we have calculated the step voltages. That means the voltage across one human step approximately or 1 meter length, and estimated the voltage that can come across one step. It has been repeated in this table here. If we have got the current I in steps of 5, 10, 40, 100 and 200, 40 being sort of 50% probable value, and step voltages at distance of 1 meter from the top pole, 2 meters from the pole, 5 meters from the pole, like that up to 20 meters from the pole. It's just to get an idea how safe it is to stay far off, how dangerous it is to when we go near. For example, if we take the 40 kiloamperes current, which is the 50% probable value of the lightning stroke current, the step voltage at 1 meter distance is 223 kilovolts. 223 kilovolts. If we go to a distance of 2 meters, just twice the distance, it goes down as the square of the distance. It comes down to 56 kilovolts, substantial reduction. We stay a distance of 5 meters, it comes down to 8.9 kilovolts. And if we are, let us say 20 meters away, it comes down to 560 volts, 5.56 kV. If you think of the worst case of 200 kiloamperes, you will see that the potential, step potential is 1000 kV plus at 1 meter, comes down to about 45 kV at 5 meters, and then even then comes to a very low value of about 2.75 kV at 20 meters. So one simple conclusion we can draw from this table is that if you stay at least 20 meters away, things are very safe, or at least 10 meters away is reasonably safe. That's the best thing that we can say. So so-called tall pole lighting protection scheme has to be barricaded for this distance. Otherwise, it can be very dangerous for two reasons. One is contact potential, which is very high, and huge currents can be driven through the human body or the animal body. And if the person is in the proximity also, there can be very dangerous potentials across each step, across one step, and it can vary from anywhere from few tens of kilovolts to even several hundreds of kilovolts at short distances, and comes down very significantly with distance or a radial distance of 10 meters may be considered reasonably safe, whereas distance of 20 meters and beyond will be quite safe. Now we have also estimated in the webinar too, what are the likely body currents if we assume that the body resistance is zero. Body resistance can be zero in wet weathers, for example, it can be very negligible. Only soil resistance determines the current that flows through the human body. Again, it can vary from distance to distance. If you again consider the same current levels of 5 kA to 200 kA with 40 kA as the mean current, mean probability current, a distance of 1 meter to 20 meters, we have calculated the likely body currents, which can range from 150 amperes to 6,000 amperes for a distance of 1 meters. It comes down as the distance. You will see that at 20 meters distance, the current can come down to 0.375 amperes, very small current. Even at 200 kiloamperes, is only 15 amperes. These things can be considered at 20 meters quite safe, 10 meters reasonably safe, but anything closer than that can be very risky. This risk level also depends on the condition of the person. If the person is a child or a female, they are far more sensitive. They may not be able to withstand this. Injuries may be severe, or it may be fatality also. If it's a patient, it can be worse still. Suppose the person has got a heart problem and a small current through the heart can mean simply fatality. Therefore, you will see that a tall pole has got two different ways of creating serious problems. One is by contact, and this by the distance, rather, I should say, yeah, by the ground current which can enter through the human body because of the potential differences in the soil. I would like to emphasize here once again, soil is not a medium of zero resistance. Many people even today have got an idea that soil has got zero resistivity, which means they may not use that word directly as zero resistivity. They may think ground, so potential difference will be zero. But immediately what it means is that its resistivity is zero. But as I told you a little earlier, the resistivities are substantial. It's not at all small, and it can provide, as we have seen the numbers, they are very dangerous potentials across one step. I have assumed a value of 1 meter, or for the current, I have assumed a distance of 70 centimeters between the steps. That's a mean value, is an acceptable value, and each step is considered as equivalent to a sphere of hemisphere of radius 7 centimeters. These are all very reasonable values, technically justifiable values. So purely on technical grounds, it is very clear that use of these poles can be extremely dangerous, firstly because of contact. Even if contact is avoided right up to a distance about at least 10 meters, because of the current entering from the ground, due to the potential differences created in the soil because of the lightning currents, the current can be substantial and there can be injury or fatality. In fact, in the second seminar, we have shown a substantial number of photographs showing the various types of injuries, which were really mind-bogglingly bad. Very, very bad injuries are there. And the list of injuries you can recall, it can be muscular, it can be mostly neurological problems, which can be lifelong or reasonably short time, sometimes only. It can be very dangerous. It is always best in our own interest to avoid the proximity of these poles. So what's the best way of avoiding this? Now, of course, here I must point out one thing. Somebody might ask, what's the critical impulse current? If the current is equal to that or higher, it is dangerous. Below that, it's not dangerous. Can we say something like that? It is not at all possible not to divide that, because when we do the experiment, depending upon the person's sensitivity, it may be fatal to him, may be very injurious to him or her, whatever it is. So such experiments are extremely risky, cannot be even thought of, cannot be thought of at all. Therefore, because of this condition, since we cannot define a critical impulse current, and since, as shown in the table 2 above, the currents can be quite substantial, the best is to avoid such contact dangers and step potential dangers. So what are the simply methods of avoiding such dangers? On the whole, it appears reasonably safe to keep a distance of at least 20 meters from such poles, whether it is so-called lightning protection pole or any other pole, for example, telephone line poles, or any other pole for any of that matter, we must keep off by 20 meters. Now, since tall poles are meant to avoid lightning, I'm emphasizing that pole in this webinar. Now, Apparently, such poles have been installed in the premises of schools and hospitals, as I mentioned a little earlier, which is very, very dangerous, extremely dangerous because children and patients are far more dangerous. They are liable to be harmed in a very bad way. No barricades have been provided. That means it is open to people, or in other words, it's an open invitation to disaster, open invitation to disaster to children, women, and patients who are far more sensitive. Now, as I told earlier, can we say that this tall pole will shoo away lightning? Hey, lightning, go away. Can we say that? It is impossible. So from webinar 1, we have seen that lightning distribution over the globe can be simply written as this simple equation: 0.1 plus 3.35 sine lambda multiplied by the factor 0.4 plus minus 0.2. Here lambda is the latitude of the place with respect to, of course, the global definitions. Now, lambda varies, as I told you, from the Arctic to the equator to the Antarctic, like that. Now, suppose you take any one place for which lambda will be some finite value, then sine lambda will be a constant for that particular position. So, if we assume that this is a constant, then the other factor is 0.4 plus minus 0.2. So, if we take the difference 0.4 minus 0.2 plus 0.4 plus 0.2 is 0.2 to 0.6. The variation can be 0.2 to 0.6. That means a factor of 1 to 3. So, for example, the isochronic level in Bangalore is 40. That's on the average mean taken over a large period. But strictly, it can vary from 20 to 60, 1 to 3 ratio. Suppose this year it is 40, next year it may be 20, it may be even 60 or 45. It may be like that. Like this. Since there's a huge variation, 1 to 3, it's not a percentage. It's a hundreds of, rather tens of percent, tens of a few factors, hundreds of percents variation. Therefore, if you look at this, we cannot say at all that the tall pole has reduced the incidence of lightning at any given area. Same given area, this year there might have been about 50 lightning incidences. Next year it might have been 30 only. The year next to that it may be 20. Like that, it will vary by itself. It's not because of the tall pole. So the simple conclusion is that any reduction of lighting incidence in a given area, it is certainly 100% certainly not due to the tall pole with cycle rim, but due to the natural variability of the lighting phenomena. I will repeat it. Any reduction in the lighting incidence in any given area cannot be due to the tall pole with cycle rim on top, but due to natural variability. I will repeat it once again. The variations are due to natural variability, not due to the presence of the tall pole. I'm emphasizing this because the data which has been cited is only for 1, maybe at the most 2 years. If they take the data for at least about 10 years, it will give some reasonably reliable values. Minimum of 5 years will give us some intimation of that, but 10 years period would be much more sensible. Now, now, the other thing is, some people may say that this tall pole is diverting the lightning. Is it a possibility? Lightning is driven by the very, very high cloud voltages, cloud potentials, which varies anywhere from 5 million to 100 million volts. That's the thunder clouds, not the normal clouds with no charge at all, but clouds that are electrified to the extent of causing lightning. So 5 million volts to 100 million volts is the likely range. Supposing the lightning stroke comes down, if you want to divert this with this several millions of volts behind the leader, what's the power that's required for this pole? Where does it come from? Where does the power come from? Energy come from? Impossible to imagine, even in the worst of dreams. It is impossible to think of it. Therefore, since Earth is at zero potential, and the charge is extremely limited, it's only the induced charge on the ground. The clouds have tens of coulombs. So because of all these phenomena, the tall pole can never reduce lighting incidence in any given area. It's a totally confusing, mistaken idea. As I told you, any variations are due to natural variability. The other possibility is this: the recording of the incidences may also be very faulty. I cannot rule it out. But natural variability by a factor of 1 to 3 cannot be denied, for any area. Even if you see the Indian standards, I don't remember their number readily. It gives the lightning stroke or lightning incidence rate at given area in India for over certain years, taken over certain years, many years. Therefore, you will see that variability is due to natural reasons and cannot be due to the tall pole. Please let us be convinced purely on technical grounds. There is nothing else in this. So in summary, I'll repeat it again. This tall pole with cycle rim cannot provide any protection even to its proximity. Forget the contacts. It cannot reduce the lighting incidence in any given area. Therefore, it is certainly not a working means at all to give any sort of protection to lightning to anybody. What's the best way? The school buildings or hospitals must be provided their own individual lighting protection, which consists, of course, of as air terminals, down conductors, and proper earthing. All the three are very important because air terminals must be having the right type of spacing. The down conducts must be properly taken to dissipate the current in an effective way so that the current in each down conductor is small, that reduces the probability of danger due to contact potentials. And then earthing must be very good. Otherwise, there can be potential differences in the soil itself, which can be dangerous. We have seen all these things in the discussion just now. We have discussed all these things. We'll go further. So what's the best way forward? It's already installed. Now we are convinced that it's not useful. So what's the best way forward? The best way, simplest way is to remove all the tall poles and forget about the illusion that is providing protection. Second possibility, if you cannot remove the poles for any reason whatever, provide a barricade. And then never put these poles in the proximity of schools and hospitals, etc. And provide barricades, particularly in case of schools and hospitals. Now I hope we have discussed this in considerable detail. If there is any technically wrong idea, we can discuss that later. If anybody feels that these technical conclusions are not really wrong, are not really right, we can discuss it towards the end. So the best way of proving it, of course, is to lighting incidence rate for about 10 years. So that gives us the average reduction, if any at all, at least 5 years. So now we are go on to another scheme which has been worldwide claimed as providing protection from lightning, reduced number but larger area protection. Again, you will see, as we will see later, purely on technical grounds, this is not a workable solution at all. We'll see that one by one, all the reasons. Now, several manufacturers of ESC-based lighting rods, they have got different shapes at the top tip, differently worded claims of superiority above the normal or Franklin rods. You'll see in figure 2 what are the different shapes. It is not much does not make too much sense. They are quite different from each other. So the basic claim is that the top end of the ESC-based rod has a device producing ionization in its immediate vicinity. That means generate electron ions density in its immediate vicinity. That's the basic claim. Now, absolutely no details or field or laboratory evidence of the working of this ionization device, whether this ionization device works properly, under what conditions does it work, under what extent does it not work. No such data is available at all. The extent of ionization or quantitative qualification of the efficacy of this ionization, not at all discussed, nowhere. Even though there are dozens of manufacturers of these ESC rods in India itself, no information is available except the claim No other thing is available. Now let us see this figure 2. See very number of shapes of these terminals, which look impressive. Unfortunately, in developing countries like ours, people are not properly educated. Therefore, they will be bowled by these shapes and by the claims. It's a foreign company, foreign know-how, so take it. So that has somehow it has been the philosophy, even though it has uh, reduced considerably over the last few decades, still it is predominant in many cases. So now, let me repeat, purely on technical grounds, these claims of the ESC manufacturers, they appear to be highly untenable, not acceptable. Details will be discussed point by point as we go further. What are the typical claims? I will repeat it. The ionization produced causes streamers to develop under the action of the arriving step leader from the cloud. They move forward very fast under the electric field of the approaching leader. So I'll repeat it. The ionization produced forms streamers at the top of the air terminals. These streamers move forward very, very fast under the influence of the electric field caused by the approaching leader, lightning stepped leader from the cloud. Now, compared to a normal lightning rod, ESC rods cause bridging with leader much earlier because these streamers move very fast. They bridge with the step leader much earlier. Therefore, they are more effective than the normal lightning rod. That's the second claim. The third claim is there is an experimental evidence is claimed, but personally, I'm convinced purely on technical grounds that this evidence is not at all adequate. We'll see in detail as we go further. This is cited in which the lightning flashover characteristics of a 2-meter gap between a 2-meter by 2-meter copper sheet as the cathode, high voltage electrode, and a 2-meter tall normal rod or an ESC rod, one at a time as LV electrode were used. The gap was 2 meters. I will repeat, on the ground plane, a copper sheet was used, probably around 10 meters by 10 meters copper sheet. On top of that, the ESC rod or the normal Franklin rod were mounted, the height of which was 2 meters. So one time ESC rod alone was mounted, another time only Franklin rod was mounted. Now let's consider ESC rod first. So on top of the rod have a gap of 2 meters, and on top of that have a 2 meters by 2 meters copper sheet as a plane sheet. Now they think that this is equivalent to a cloud. A cloud is at least 2 to 3 kilometers away. What the ESC rod sees in reality is the approaching leader. It does not see the cloud. It sees the electric field created by the leader, which is at a very high potential. Of course, the potential of the leader is created by the cloud and cloud potential. There is no doubt about it. But the electric field at the ESC rod tip is due to the leader and not due to a cloud itself. Therefore, one of the important points to note for us is that the copper plane used 2 meters by 2 meters plane is not an appropriate representation of the leader. That's the most important, one of the important points. Now, it is stated that for a certain flashover voltage, we will see a little later what's meant by flashover voltage under impulse voltages. You apply an impulse has got a peak value. The time from zero to peak of the impulse wave is known as the time to front. And then subsequent to that, the voltage decreases exponentially. That's known as the tail of the impulse wave. And then a flashover occurs. That means voltage collapses to zero because of the flashover. This is known as a chopped wave. What they say is that in case of the ESC rod, this flashover occurs 10 microseconds earlier than in case of the normal rod. I will repeat it. In the case of ESC rod, copper plane, let the flashover occur at time t1. In the second case, when you have the normal rod, the flashover occurs time t2. So time t2 is longer than time t1 by 10 microseconds. What are the implications of this? We will see presently. Yeah, a particular company, Applicaciones Technologicas, claim that they design and supply ESA rods which can flash over even 90 microseconds ahead. Previous experiment, I said they claim that it's 10 microseconds earlier. Here they say this particular company says that their ESC rods are available which have got different time differentials even up to 90 microseconds. But absolutely no clue has been given as to how this is achieved. How this is achieved, we don't know. Suppose somebody says, you eat one plantain, you'll not be hungry for 1 week. Will we accept that? This is something like that. I do this, it'll flash over 90 microseconds earlier than the ordinary rod. It's a statement, not at all substantiated in any way. To go back again, suppose I eat one plantain, it's very special plantain. I will not feel hungry for 1 week. Is that acceptable? No way, is it not? That's a very commonplace type of analogy. Of course, no analogy is really perfect, but what I mean to say is that yes, the rods are claimed to flash over a certain time earlier than the normal Franklin rod. We'll see the further implications a little later. This is the table where I said the Applicaciones Technologicas has given a whole table where the time of advance is 15 microseconds, 30 microseconds, 40 microseconds, and 60 microseconds. They have given the data like that, but absolutely no proof or no evidence. Forget the proof, no evidence at all anywhere. Oh. In this connection, you will be surprised to see a very detailed and extensive work carried out by Allen and Micropoulos on what's called the dynamics of streamer propagation in air. Dynamics, the movements of streamer propagation in air, is published in Journal of Applied Physics, Journal of Physics D, Applied Physics, volume 32, 1999, pages number 930 to 919. The experimental setup is shown in figure 4. You can see the figure here. On the upper part, you see the experimental setup. There are 2 electrodes, one at the ground level. See, this represents the loads electrode, which is positive. In the center of this plane electrode, there's a small hole through which a small needle electrode is inserted. The tip of this needle electrode is flush with the plate. As we'll see a little later, this needle will be fed with a rectangular pulse of 4 kilovolts of 2 different durations, 270 nanoseconds and 135 nanoseconds. We will be concerned with the 275 nanoseconds, which is the best we can imagine from the ESA rod manufacturers also. Now this ground plane is like this with a trigger electrode. We will call this the trigger electrode. The trigger voltage appears between the needle and the plane. And then we have got at a gap of 12 centimeters, may appear small, but you will see that it is quite significant for us. There's another electrode like this, and then a voltage is applied to this one, a negative voltage. So in some sense, it represents the cloud. Let me say, in some sense, it represents the cloud, in the sense that it is negative. So the ground plane is positive with respect to this electrode. That means we have got the cloud and the ground. In the case of the ESA rod experiment, I said that use of copper line is not proper, but I will justify this a little later, only for the results of this experiment. So now there are 3 photomultiplier tubes, 1, 2, and 3. Photomultiplier tube 1 has set its beam level at the top of this ground plane. That means you can say at the tip of this trigger electrode. I'll repeat, the photomultiplier tube beam is set permanently in level with the trigger electrode top. Then the second photomultiplier tube is fixed permanently so that its beam is coincident with the top plane of the upper electrode. So these two are fixed. The third photomultiplier tube is here. it has got a variable position starting from 2 centimeters above the ground plane to 4, 6, 8, 10, 12. It can be moved anywhere precisely like this. Now, what it does is, when the trigger pulse is given there, this will see whether there is any streamer formation, any streamer movement here that will be monitored by this middle photomultiplier tube. So I will repeat this portion. This photomultiplier tube in the middle, there's the photomultiplier tube 3, is here to monitor the progress of the streamer from the ground electrode upward towards the cloud electrode or the negative electrode. So now, at a given voltage of DC, I will try to give this signal and see whether the streamer will propagate at all or not. At what voltage level it will move 2 centimeters or 4 centimeters like that. For each position, I will find out whether the streamer can propagate or not. There are examples of this here. 3 examples are there. So this time taken here 620 nanoseconds. This is only a typical mode of photomultiplier outputs are shown here. Now we will see, for a given voltage here, will a streamer occur here? How much can it propagate? Has it propagated for 2 centimeters or not? And then the important point is this experiment at the given spacing and at a given voltage level is repeated 20 times. It's a very important point for us to note. So it is, statistical behavior is completely studied. It's not avoided. So at each position, for a given voltage here, the pulse is given and we see whether the streamer has propagated for that particular distance. For example, it may be 2 centimeters. Apply a certain voltage there. For example, stress being equal to 450 kV per meter or whatever it is, and then apply 20 pulses and see how many times it has propagated to that distance or not. It's a very, very beautifully designed experiment. Now we'll see the results presently. We'll see that it's really exciting to see how things go. So to give some more details, the cathode potential, that's the cathode electrode representing the cloud, was adjusted in steps in the range of 450 kilovolts per meter to 800 kilovolts per meter. Please remember that the spacing between the electrodes is only 12 centimeters. So corresponding to 450 kV per meter, the voltage would be 450 multiplied by 12 divided by 100. That means approximately about 0.45 into 12 kilovolts. Like that, for each given field, I know how much it has propagated. Even though the experiment have been considered for both 270 and 135 nanoseconds, we'll be considering more with respect to 270 nanoseconds. That is a higher one because that gives a higher propagation. Obviously, higher ionization, therefore higher propagation, higher velocity, all those things. So now, I'll repeat it again. I have said that earlier. For a given pulse of width 270 nanoseconds, 4 kV magnitude, trigger pulse is 4 kV in magnitude, and duration is 270 nanoseconds. And considering a given electric field strength, that means for a given applied voltage, the propagation distance of the streamer was studied and found probabilistic. The probabilistic nature is studied by applying 20 voltage pulses to the trigger electrode at that particular voltage level. The experiment results are here. They are very interesting results. So now, here are the results. Beautiful results are there. We will consider the right-hand side of the figure because that corresponds to 270 nanoseconds width. For example, let us say here, I have applied only roughly, let me say about 170 kV per meter. That's the electrical field that's applied. There's a uniform field across the full 12 centimeters length. What is the probability of propagation? It's just 0 plus. You can see the triangular point is just above 0, 0 plus. So if you want to have 200 kV per meter stress, if that's the pulse given, then you will see that the probability of movement is approximately 45%. So if I apply 20 pulses, 45% of that means 9 pulses alone travel up to that distance. 9% of that alone will travel up to that distance of, this is 2 centimeters. So if you want to propagate beyond 2 centimeters, you have to apply a higher voltage. It's a very important point for us to note. If you want to apply, if you want the streamer to propagate by a larger distance, we have to apply a higher field. Higher field, that's very important. For example, if you go further again, you will see that this is for 4 centimeters. The last one is for 12 centimeters. 2, 4, 6, 8, 10, 12. This is for 12 centimeters. So if you want to see that the pulse propagates only 12 centimeters, I am not interested in its propagating only 2 centimeters or whatever it is. So what voltage should I apply, and what's the, at each voltage, what's the probability? For example, if I apply here something like 380 kV per meter, that's the electrical field. What is the probability? 0 plus. You see at this point, that square is just above this baseline. That's the probability is 0 plus. If you apply 20 pulses, it may or may not come out at all. Therefore, if you want to see higher propagation, I have to apply a higher field. For example, suppose you consider this point where the probability of propagation right up to 100% is considered. For this, the voltage is approximately corresponding to roughly about 470 kV per meter, roughly. I've got the table there to give more data. So you apply approximately 470 kV per meter electrical field. The trigger pulse can move up to full 12 centimeters. The probability is not 100% here. It's according to them 97.5% only. It's not right up to 100%. They have gone up to that particular level. So now, what's the important conclusion based on this? For a given pulse, for a given trigger pulse, let me properly put it, let me give for a given trigger pulse, unless the applied field from the from above has got a minimum value, it will not propagate. Or if you want it to propagate, I have to apply a higher field. This is the important conclusion for this. So what this particular mean, we will go to this one. I have given some extract from this table. Again, the pulse is 4 kV, duration is 270 nanoseconds. The probability of propagation and the electric field strength are given here. 0 plus probability for 2 centimeter propagation. For merely 2 centimeter propagation, I apply a field of at least 170 kV per meter for just 0 plus. It means out of 20, one may propagate, the other 19 may not. If you apply another 20 pulses, maybe even that may not occur. On the other hand, if you apply 190 kV per meter, 50% is the probability of propagation. That means out of 20 pulses, 10 are likely to propagate up to 2 centimeters. Now let's consider the full distance of 12 centimeters. You will see that at 375 kV per meter applied field, the probability of propagation is 0 plus. That means maybe 1 out of 20 or 0 out of 20, maybe 1 out of 20 again, like that. If you go to 395 kV per meter, 50% probability is there, which for it to travel at a full distance of 12 centimeters. Like this, if you want to make it travel full 12 centimeters with almost certain probability, we have to apply a field of 405 kV per meter. You will see that even though there is an applied ionization field, a minimum field from the external source, that's the cloud electrode, is essential for it to propagate that distance. If we stretch it to our streamer electrode, what does it mean? The streamer has got a known ionization pattern. It cannot be changed. Now for that, for it to propagate properly, there must be a minimum field. There must be a minimum field. If that minimum field is not there, it will not propagate. We'll see more interesting things. This is the first very important thing for us to understand. If the minimum electric field does not exist, the streamer will not propagate, or the probability of propagation will be very limited. If the field is higher, the probability of propagation is higher. So these are the same conclusions I have put down here. See, since ESC rods have not specified any data on the internal pulse, it's very doubtful whether the streamers can propagate at all. We don't know. We cannot say anything. They claim. It's only a claim. Maybe a very, very hollow claim. Maybe partly right. But on the whole, it looks extremely doubtful whether it can propagate at all. There's another point we'll see equally important or even more important as we'll see a little later. What I was to emphasize here is that here, because the electrode pattern, plane at the top, plane at the bottom, the field is nearly uniform. So even if the field is uniform, it's unable to propagate. It's unable to propagate even if the field is uniform. But in the case of lightning, the potential rises in a short time of the order of a few microseconds, then starts declining very rapidly. In about 100 microseconds, it goes down to zero. So instead of a uniform field, rather constant field with respect to time, here we have got a time varying field which drops rapidly. So how can the streamer move when the whole field reduces? It has to reduce its velocity and then stop after some time. It's a very, very important conclusion. We'll see that again further. So the results quantitatively confirm it's both obvious and intuitive that the velocity of propagation is strongly dependent on the electric field at that location. It tends to stabilize after propagation around 6 centimeters in this particular case. So I'll show the figure there. Beyond 6 centimeters, it needs higher and higher fields, and then the velocity also stabilizes. So from the same set of data, they have written down here beautifully the velocity of propagation. If you think of just 450 kV per meter, the curve is A, this is the curve A. So you will see that at 1 centimeter propagation, the velocity of propagation is less than 5 to 10 to the 5 meters per second. But as the spacing goes higher for the same pulse, this is at 1 centimeter distance. At 2 centimeter distance, the velocity has fallen down. That means the streamer propagation has come down, velocity has come down. So you'll see that as you go further with spacing, at 5 centimeters, it has come down to almost half. That means 2.5 times 10 to the 5 meters per second. So you'll see that beyond roughly about 6 centimeters, the velocity is nearly constant at some value, which is here between 2.5 for curve A and about 3.5 for curve C. Now, if you think of a much higher voltage, for example, 750 kV per meter round figure, 748, I will read it as 750. This is the figure. Now, if you see the figure is really horizontal, even though they have given this, you see the spread here, you see the spread here, see the spread here, you can say it's nearly constant, approximately at about 7.5 or 7.8 into 10 to the 5 meters per second over the entire region, provided the field is very, very high at the 750 kV per meter, 7.5. Velocity is 7.5 10 to the 5 meters. The field is 750 kV per meter, which is an extremely high field. Computer simulations have shown that after a height of about approximately half a meter, the field at the tip of a rod, whether it's ESE or Franklin rod, it drops down to very low values if the streamer, if the leader is far apart. We'll come back to this point a little later. So now I have taken out from that figure some data which is easily understandable. At a field of 450 kV per meter, the velocity at a distance of 1 centimeter is 4.7 in 10 to the 5 meters per second. And at 12 centimeters, it dropped down to less than half, 2 in 10 to the 5 meters per second. Now, if you come to 650 kV per meter approximately, it was 6.2 to 10 to the 5 bits per second at a distance of 1 centimeter. It has come down by substantially, maybe around 40%, 30%, 5 10 to the 5 meters per second. At 750 kV, it's more or less constant. You saw the spread, which I emphasized there. I have taken out the data 7.5 and 8. But if you see the figure again, back, I have to go back. Okay. You see that if you see the total spread, it's more or less constant only. Even though I have taken here this point, here I have taken the lower point. That's why you see that there's some difference, 7.28, but it's more or less constant at 7.5, 7.8, 10 to the 5 meters per second. So what are the conclusions now? Even at a very high field of 449 kV per meter, the velocity is limited to 225 meters per second after propagating 12 centimeters. Beyond that, it's likely to fall to zero very quickly. This is in spite of the fact, I have emphasized this earlier also, in spite of the fact that the field is constant, it's a uniform field over the complete distance. That means over the complete distance of 12 centimeters, the field is uniform. Whereas in the case of real life, the field is highly non-uniform. Highly non-uniform. The field is very high at the tip of the rod, comes down to very low values, less than 1/10 almost, or even less at a distance of even 1 meter. Even a distance of 1 meter. Therefore, the velocity of propagation of the streamer drops significantly to zero. Propagation will stop after a short distance, typically after about a half a meter or at the most a meter. So this is in complete conflict of their claim. They said it moves very, very fast. That very, very fast is not at all practical in view of this particular set of experiments. The experiments we have seen already, very, very well planned, very, very carefully conducted. All the probabilistic variations are very thoroughly considered. So now this very important and very significant fact is not at all considered while making the claim of a high velocity of propagation of streamers at large distances from the tip of the ESA rod. So how can it function in the field? Next one, we consider the claim of something like 10 microsecond, commonly claimed, and then the French company Applicaciones Tecnologica, it can be up to 90 microseconds. Now, I'll come back to the same point here. The electric fields of a conical point plane is very different from conical point rod. Now, this remember, the experimental setup is very different. I'll come back to this figure, please see this. What they have used is a 2 meter by 2 meter copper plane here to represent the cloud, negative. And then the rod, ESC rod or Franklin rod. So this is a plane point or rod electrode arrangement. If you apply a certain field, you'll see that the field is uniform in this range, but non-uniform here, no doubt. But you have got a rod and a rod, it's highly non-uniform, much more non-uniform than in this case. Now, their experimental claim of 10 microsecond advance firing of the ESA rods is based on this type of field. But in reality, the leader can be represented at the most by a rod. The leader diameter is typically about 12 to 15 millimeters diameter. So we can consider a 16 millimeter diameter rod here and think of it as a leader far more realistically than this plane, 2 meter by 2 meter plane. In which case, you will see here, the field is far more non-uniform here. That means it will be very high at the tip, but drops very rapidly to very low values as we come even a short distance. Let me say, for example, if the diameter of this is 3 millimeters, if you come to about 10 times that, about 30 millimeters, the field is almost half. If you come about, for example, half a meter, that means 10 to 30 centimeters, it will be much, much lower than whatever the field was here. That means obviously, if the field is lower, the propagation velocity must drop. We have seen that experimentally also. It's intuitive also. If the applied field is lower, the velocity must be lower. Exactly, just as in a car. You press the accelerator more, it has to move faster. If you don't press the accelerator, it may come to a halt. Like that. It's an analogy, as I said, analogies are never perfect. But to illustrate one simple point, I have cited that analogy. You'll see that if the field here, the tip is very, very high, but comes down to very low values as you come forward. Now, if the rod is by side here, what will happen? The experiment says it has been placed like this, one above the other. Sorry, in this case, it is like this. And then you get a 10 microsecond time differential. Supposing we had a rod, will it be the same 10 microseconds or not? We don't know. In case you consider real life, the leader may be coming from this side like this, or it may be coming like this, or it may be going away like this. So how will the field be? So what will be the direction of propagation? What will be the magnitude? Everything is total chaos, Total chaos, nothing more, nothing less than that. Therefore, the claims are also very, very unfounded, very, very illusory, not at all supportable by any experiment at all, unless they do it on a far more realistic case than this, and considering the rod at various positions, various angles, like unless they do it, it cannot be believed even by 0.01%. It cannot be relied upon. So now this summarizes the whole lot. Very important aspect is the voltage flashover time characteristics of the gaps. Whether GSC rod or plain rod is ground electrode. Top rod should be HV negative electrode. Now this is only repeating what I have been talking. Essentially, it means that two things. One is plane is not acceptable as representing the leader coming down. The second is the field is non-uniform because of that. The third is voltage is time dependent. It rises to the peak value and then goes on reducing. Therefore, the velocity also reduces. It's a time varying field. That's what I have put down here. It's a time varying field. We will see here. So I'll show you some figures also, the time variations. In the laboratory, remember this is it, not kit. It is it. It is therefore not surprising that breakdown characteristics of the air gaps or any gaseous gaps and impulse volts are also statistical. What I mean here is that even if you take a simple rod gap, the behavior is highly statistical. If it is ESC rod, the statistical behavior, according to them, reduces drastically. Now here, it may not at all, because another set of experiments by Nijdam and others have shown that some amount of excitation is not at all helpful. In fact, it may reduce the velocity of propagation because the field at the tip is reduced. Now, let us see for our further understanding, what is this voltage time characteristics? What do we mean by this? Suppose you have a rod gap, let me say a gap of 2 meters or 5 meters or whatever gap. If you apply higher voltage, the time to flashover reduces. If you apply still higher voltage, the time to flashover still further reduces. What is this? I would like to illustrate it by a figure. You see, this is what we call a full lightning wave. It increases exponentially from 0 to the peak in a short time. This time in which it rises is known as the time to front. And then it starts reducing like this. This reducing portion of the wave is called the tail time. So this is the time to front. The time in which it reduces to half the value is known as the time to tail. So the time to tail is the time in which the voltage reduces, of course, on its tail to half its peak value. For example, this one is the time to tail. So now let us take the case of a chopped wave or a flashover occurring. You see here, I apply this to a gap, the same voltage wave. You'll see that it goes to the peak, comes down, and the gap may flash over somewhere here. So this is what we call a chopped wave. It is chopped. It has flashed over. So voltage has come down to 0 very rapidly, reaching here down to 0. This is called a chopped wave. The time from 0 to this instant where the flashover has started is called the time to chop. So this voltage and this time to chop together form what we call the voltage time characteristic. Suppose I increase this voltage to a higher value, for example, up to this value, you will find that it breaks down much earlier. So you'll see that higher voltage and shorter time to chop. So like this, starting from a very low probability, I quote a high voltage and a very high probability of flashover. We plot that curve of the peak voltage before flashover, and then the time to chop, we call that the voltage time to flashover characteristic. Now, the important point for us to note is that even for a given magnitude of voltage, supposing I apply 10 pulses, All of them may not cause flashover. This is the very, very important statistical behavior of breakdown under impulse voltages, under transient voltages in general, impulse voltage in particular for our application. So now, for a given voltage also, this time to flashover may go on varying in a fairly narrow range. Now, the voltage, at least the probability of flashover is 50%, is known as the critical flashover voltage. Let me repeat, the critical flashover voltage is that voltage at which, if I apply, let me say, for example, 10 impulses, 5 may flash over, 5 may not flash over. I will repeat once again. If I apply a large number of pulses, some of them may cause flashover, some of them may not. This is because of the high probabilistic nature of impulse breakdown of gaseous gaps. In particular, of interest to us is the air. So now, here you have got what I have described to you as a voltage time characteristic. For example, at this voltage level, the time to flashover is given here. This flashover has occurred here. It has drastically come down. If I go to this voltage, the flashover has occurred here. So that's a point on this curve. You see this point on this curve? And then if you take this point, the peak voltage, the time to flashover, I get this point. This is the time to flashover. This is the peak voltage. I increase the voltage further. This is the peak value. Time to flashover is reduced. So I get this point. So you still increase it further. I get this voltage and this time to flashover. So this curve is known as the voltage time to flashover characteristic. But remember, at each voltage, flashover may occur, may not occur. Therefore, you will find that there will be a spread here. There will be a spread here. There will be a spread here. There will be a spread here also. There may be some 10 points here, 10 points here, 10 points there. So it's highly probabilistic. The important point for us to note is that typically the 50% breakdown voltage occurs approximately in the time range of 10 to 15 microseconds. 10 to 15 microseconds, a variability of 5 microseconds. That's the voltage at which, that's the time range in which the typical 50% breakdown voltage occurs. So in such a case, if there is a variability of plus minus 5% to 50% almost in that particular voltage level, how can you assure a time differential of 10 microseconds for the ESC gap compared to your odd gap? How can you do that? You cannot. I cannot. Why about you? I cannot assure that. If the ionization is there, we have seen of the earlier experiments by Allen and Micropoulos, again the breakdown is probabilistic. And then the velocity of propagation reduces because we're reducing voltage and impulse field. There it was a uniform field like this, constant field. It's a reducing field, so velocity of propagation reduces. So you'll see that because of this additional behavior of the voltage time characteristic, you will find that there's an additional factor which declares that an assured 10 microsecond differential is simply impossible. Simply impossible. If they provide their gaps and standard rod gaps, if we take it to a laboratory, we can demonstrate it by a series of well-planned experiments. It is possible. Lightning test facilities are available, about which we will talk presently. Such facilities are available. If they are willing to spend the time and money, we are prepared to do that experiment and see how solid is their claim. How solid is their claim can be verified by these experiments in their own presence or in the presence of their clients, whatever it is. Anybody can witness those experiments. So now, going back again, the time from 0 to instant flashover is called the time to chop. A graph showing the peak voltage before chopping, and the time to chop is commonly referred to as the voltage time characteristic. We have discussed that at length. This is the full wave. This is the chopped wave as an example. This is the voltage time to flashover characteristic. And then important point which is not shown here is at each voltage, the time to flashover has got a spread. And the voltage to flashover at that particular point also changes. So this whole thing is not a simple line like that. There's a spread of data at each voltage here. At each voltage, there is a spread of data. Therefore, you will see that it's not a simple, beautiful curve like this, but it is a mean of the values plotted like this. But important point for us to note is that compared to Allen micropulse results, here the voltage is not constant. Therefore, the velocity of propagation being dependent strongly on the field, the propagation of the ionization streamer from the ESA rod will also fall very rapidly. The time to chop is about 50 microseconds, like that. There's yet another even more important point, as we'll see a little later. So just to repeat again, at given voltage level, usually 10 impulses are applied at intervals of 15 seconds to 30 seconds. It is seen that even for nominally the same peak voltage value of voltage, the times to chop show a statistical behavior. How can anyone ascertain a definite time differential of 10 microseconds? It simply cannot happen. Therefore, it's simply not acceptable. Purely, remember, 100% purely on technical grounds which can be demonstrated in a laboratory. So now, yet another point. In the laboratory, a standard voltage wave 1.2 microsecond front time and 50 microsecond tail time are used. This wave shape is generally shown there, but the front time can be 1.2 plus 30% microsecond. That means rather the tolerance is plus minus 30%. That means it can vary from 0.84 to 1.56 microseconds. This from laboratory to laboratory or setup to setup. For a given setup, it will be constant. Similarly, the time to tail has got a tolerance of 20%. That means 40 microseconds to 60 microseconds. Now, we'll see just a little later. This is a standardized lightning impulse wave for tests essentially on power transformers. The real life lightning wave is far from this, very, very far from this, we'll see presently. Here I have shown totally 4 lightning induced voltage waves. The top 2 are negative polarity voltages. The bottom 2 are positive polarity impulse voltages. Please see the time scale here is in milliseconds, 0.05 milliseconds, that means 50 microseconds. That means up to this point, it's 50 microseconds. Is this 50% of the peak? 50% of the peak is somewhere here. So it's not time to tail 50 microseconds, it is not there, it's much longer. So if you see here in this, here the time scale is 0 is 0.5 milliseconds. That means this 500 microseconds. So the time to tail is of the order of much lesser than that. So this wave is typically a little better than this. So what I should say here is that time to front, time to tail of the real life lightning is unidirectional substantially and oscillatory. Oscillatory but unidirectional. Oscillations are only one polarity. This is for the negative polarity, just 2 pulses. So these are 2 more pulses. Positive polarity is there. You see that there are a lot more of oscillations here. And then you will see again the time scale is 0.05 milliseconds. That means this is about 50 microseconds. You see around 50 microseconds here, there is a huge oscillation. So what is it that you take here? Similarly here, what is it that you take? 50% is somewhere here. What is it that you take? The front is substantially good, beautifully I should say. 50% is here, but where's the tail time? So in reality, the time to front of a real life lightning wave is typically around 5 to 10, 15 microseconds. The time to tail, if you want to look at that, it can vary from 15 to 20 to even hundreds of microseconds. So if in a laboratory and standardized conditions, if the time differential of 10 microseconds cannot be verified between the ESC rod and the normal rod, what can you say of its behavior in such highly non-reproducible, highly unidirectional but oscillatory wave shapes? What's its behavior? What can anybody say about this? Nobody can say anything about this, because real life single lightning to say another lightning can be very substantial difference. Therefore, the performance can also be extremely different. Extremely different. How much? We don't know. Now, one more important point is the lightning protection. As we discussed in webinar 3, The last step, the striking distance is very important. That's what is used for designing the lighting protection system using the rolling sphere technique. There it was reported that the velocity of propagation of the leader during a step is of the order of, now this is from the literature. I'm sorry I have not mentioned the reference here. I don't have it ready now. Therefore, I have to just state that typically during the step, the velocity of a leader is approximately 5 times 10 to the power of 7 meters per second. That means 50 meters per microsecond. 50 meters per microsecond is the velocity of the leader development during its final step. That means duration of each step is much less than 1 microsecond. Typically, maybe if you consider a step, last step of 50 meters, then only it will be about 1 microsecond. If the velocity is higher, it will be less than 1 microsecond. It will not be less than this. It will be, if any, more than that. Now, what distance can a streamer travel at its velocity of 8 times 10 to the power 5 meters per second? Remember, this data we have taken from Allen and Micropolo's experimental results. At 758 kV per meter, the velocity was approximately 7.8 times 10 to the power 5 meters per second. I have rounded it off to 8 10 to the power 5 meters per second. So at a field of 8 kV per meter, this is the velocity. Now, what's the time? What's the distance it can travel in this 1 microsecond? At the most, it's only about 0.8 meters per microsecond. That means it can travel only 0.8 meters. So if they say it can travel long distances, what's that long? Has it any meaning? It can travel when the step leader, when the lighting comes down and joins the leader, joins the streamer by a distance of 50 meters, comes down and joins. It travels 50 meters and comes down and joins the streamer. The streamer might have traveled only about 0.8 meters. It would have traveled only about 1 meter. So now, again, the point is, if the velocity of the leader, which has been measured and to be about 5 times 10 to the power 7 meters per second, that means 50 meters per microsecond. The last step, if you assume it's only 50 meters, the duration of the last step is only 1 microsecond. In that 1 microsecond, the streamer from the ESC rod can travel at its the highest velocity. Even if you assume it's 10 to the power 6 meters per second, it can travel only 1 meter. So the step leader will travel down 50 meters. The streamer will travel only 1 meter. So it's this claim that the streamer from the ESC rod can travel long distances and meet the leader so that it does not go elsewhere. It holds it there. It is simply not acceptable. Simply not acceptable. Simply not acceptable at all. That's what anybody can say from this. Now, you might question me, then why is it that the standard lighting voltage wave has got 1.2 microseconds front, 50 microseconds tail time? If the real life is very different, how much is that? We'll see that presently. So some of the important points I will repeat. The real life lighting impulse wave is oscillatory and predominantly unidirectional. We have seen already the figures. It is not possible to define with certainty a time to front. Even with this tolerance of 1.2 plus minus 30%, it's not at all proper. Then why is it that is fixed? We'll see that a little later. Because of the significant oscillations, not at all possible to define a time to tail, appears to be at times quite short. I have seen at one place, in fact, one of the figures was showing 100 microseconds, 150 microseconds. Therefore, the claimed time differential of 10 microseconds makes absolutely no sense. No justification can be given for this at all from based on the experimental facts. Experimental facts. So in the light of the above, to me it appears highly questionable that ESC rods cannot function in the real life as claimed. So it appears unquestionable. Nobody can question it, that ESC rods cannot function in real life as claimed. Field experience, many failures of ESC rods in protecting against lighting has been reported. Many has been reported. Now in this, I think probably it's good to know that these ESC rods are mainly used only in developing countries like India and Malaysia. Whereas in other countries, European countries and USA particularly, ESC rods, the rule is that if you want to use ESC rods, use them. We cannot prevent you. But the location, etc., must completely follow the same norms as for the normal rods, or in terms, in brackets, Franklin rods. It cannot make any distinction. Why? 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 Because it's impossible to prove that ESC rods are superior in any sense. Now, these figures, you see there is a ESC rod here. The damage is here at this corner. It looks as though it's about 45 degrees itself. Looks that way. It may be even smaller. Therefore, you will see that the corners of the building are more attractive than the ESC rod for the lightning. So ESC rod has not proved to be efficiently attractive for lightning at all. So it is not really meeting the claims at all. Another case is a broader building. ESC rod is here. Again, the damage is here. So the claim that ESC rod can give broader coverage, more efficient, much earlier, all that are really not verified even practically. Now, again, more cases. This is a repetition of the earlier one. ESC rod, corner damage due to lightning. Now, this is another house. They say broad area coverage. There's ESC rod here. The house has got damaged at this corner. So we'll see that the normal corners and edges are far more preferred attachment points for the lightning than the ESC rod in many such cases. Now here, now in this figure, this is a published paper. So references are there in this also. You can see the claimed area of production as per the manufacturer is shown by this sort of parabolic figure. ESC rod is at the top. The area of production is this parabolic curve. All the volume within that is supposed to be protected. But you will see that the damage have been reported to have occurred here. Another figure, same thing. Damage have occurred both here and here, 2 levels. Same building at 2 different places. So ESC rod, what has it done? Nothing. It has witnessed. That's all. Nothing more. Hey, what happened? I have to go back. So having seen that real life failures of ESC rods, failure to protect, failure to meet the expectations is there here. Absolute proofs are there. Nobody can deny these things. Now, after having discussed the ESC rod performance at length, we'll see what's the possibility of its testing in a laboratory and what are the possible tests. The laboratory we are going to discuss will not necessarily discuss the ESC rod at all, but ESC rods also can be tested in those laboratories. That's what I'm trying to say now. So in general, we discuss the laboratories, their facilities and capabilities. So now, in real life, cloud electrification is very high. Voltages up to 100 million volts are possible, and they break down the air between the cloud and earth. The strokes carry very high currents. Lowest is around 2 kiloamperes. The highest is around 200 kiloamperes. The highest recorded negative voltage, negative current wave is about 212 kiloamperes. For positive strokes, highest recorded has been 360 kiloamperes, but since they are very rare, for all practical applications, only the negative strokes are considered. Now, in principle, it's not practical to generate both these high voltages and high currents. Possible in principle, but not practical. If you are prepared to spend some 100 crores on one laboratory, it may be possible. I can probably do it myself. But if you can give me 100 crores, possibly it can be done. So a single generator having such high voltage, having such capability of such high currents, it's in principle possible, but not practical. Certainly not economical. Now, therefore, what is done is the voltage is generated separately. in what we call an impulse voltage generator. Up to 10 megavolts are available in the world, 10 megawatt impulse generators. Now, these are what are called nominal voltages. Typically, the efficiency is between 80% to 90%. So you can say the output voltage can range, maximum output voltage can range right up to about 9 megawatts. But in these voltage generators, the current is limited. Typically, maybe 5 kiloamperes to possibly up to 20 kiloamperes. In particular, some aspects of performance of air terminals, which are used for attachment point determination, flashover characteristics of insulators, insulator strings, protective gaps, etc., can be studied. Now, these air terminals are not the Franklin rods or ESC terminals. Now, what I am saying is that if you think of an aircraft, which is a very odd-shaped body considering normal building, where does the lightning most probably hit? For deciding such attachment points, we use these lightning test facilities, and either the full-scale models of the aircraft, for example, or the scaled models are also used quite often. Now, for current, you have got separately current generators. I must emphasize again here, which I have done many times earlier, voltage causes breakdown of the insulating path and allows the current to flow. And this is the current which always does the damage. It's always the current which does the damage. The damage done by the voltages, it creates a path for the current to flow, and the current does the damage for us. For example, whether it's a fire hazard, or a building damage, or a human fatality, or whatever it is all done by the current. Current capability is relatively very easy to go up to about 200 kiloamperes or even 300 kiloamperes. Wave shapes and test object characteristics are very important. Impulse voltage, lightning voltage wave shapes, and then current generation wave shapes we'll see presently. In the case of direct strokes, as already mentioned, the real-life lightning wave shape is oscillatory but unidirectional. There are what are called pre-stroke bursts. Before the main return stroke, there are several small lower voltage bursts which occur, which are known as pre-stroke bursts. And then along with the first return stroke, there can be several return strokes per flash. So typically, the times to front range from about 5 microseconds to about 10 microseconds. The four figures I showed you, typically about 5 microseconds, and in one other case, it may be around 10 microseconds. The time to tail varies, since it's oscillatory, very difficult to define with any emphasis. Typically, you can say it's around 30 microseconds. Then why do we use longer times to shorter times to front and longer times to tail is a big question. Now, the test wave shapes used in the laboratory, this is the most important consideration. This test wave should be more severe on the test object than in the field. The most common and most critical test object in the lightning test are the power transformers, the high voltage, high power transformers, because they face lightning very often, and if the transformer fails, millions of users of power can be affected. Therefore, that's the most critical component of the power system, and therefore that defines how the lightning wave shape is defined for testing of the power transformers, and therefore for practically all other equipment. So now, if you think of a lightning wave, you see this is the real final stroke. It can be oscillatory, like this tail, and then one more stroke like that. Now, these strokes occur before the main burst. These are known as the pre-stroke bursts. I have only told you time to front is the time from 0 to the peak value. Time to half value is like this, time to tail. The envelope gives us the shape, but the magnitudes and times to front we decide based on, as I told you, higher security concerns for the equipment under test. Sharper the time to front, more severe the stresses on transformer windings. Is a very important point to first note. If you apply very sharp time to front for a transformer winding, there will be concentration of the voltage stress at some parts of the winding. Therefore, that can fail. To avoid this, in the laboratory, we use much sharper time to front than in real life. That's why even though the real life time to front is about 5 to 10 microseconds, the laboratory we choose 1.2 microsecond as the standard, plus minus 30% as the tolerance. Earlier, 50% was the tolerance, but it has been reduced to 30% because generation has become much more simple today. Therefore, the time to front should be smaller than this to make it more severe on the transformers. Therefore, it's 1.2 plus minus 30% time to front. On the other hand, if the voltage exists for a longer duration, the probability of incident failure is higher. That means the longer time failed is more severe on the transformer to be tested. Therefore, you will find that it's about 30 microseconds to 35 microseconds. The real life standardized time to tail is 50 microseconds plus minus 20 microseconds. So even the minimum 40 is higher than the 10 microseconds in the real life and can go up to 60 microseconds. These are much longer than the real time of 30 microseconds or even shorter. So now this is how the wave shape is seen. 0 goes to the peak in 1.2 microseconds, then reduces to half the value in about 50 microseconds. Now, in particularly earlier times, when you do a test on any equipment in the laboratory, the 0 was not easy to identify. Therefore, what was done was they identified the 10% of the peak value, 90% of the peak value, they joined the two and made it beat the peak value. And this time between these 2 points is known as the virtual time to front, and that is what we call the virtual time to front of 1.2 microsecond plus minus 30%. And this gives us a little longer, slightly longer real time to front, 0 to peak, typically around 1.7 to 1.8 microseconds. On the tail again, it's from 0, either 0, this 0 is immaterial because there is 50 microsecond. A small variation here is not of great importance. Now, how do we generate this voltage? I'll go through only the principles because the webinar main purpose is in the other directions we have already been discussing. Here, essentially, the test facility, what it's capable of is the main point under discussion. Now, what we do is we have got a huge transformer, a huge capacitor, charged to the required voltage, and then it discharges when commanded. When the switch closes, discharges through a parallel combination of a capacitance and resistance. So I have got C1, R1, we call the discharge resistance, R2 is the time to tail resistance, the C2 is one of the front time resistance. The front time is dictated by R1 and C2, R1 and C2. The tail time is dictated mainly by C1, R1 plus R2. So we get a wave shape of this kind very easily in the laboratory today. Very, very easily we can do that. Typically you will see that R2 is much higher than R1. C1 is very much higher than C2 because front time is decided by R1 and C2. Since it's very small, R1 and C2 are very small. This tail time is dictated by C1 and R1 plus R2. Therefore, you will find that C1 and R2 in particular are very much large compared to the other resistances. Now, if you have got a single stage like this, it's not possible to go to what is the order of, say, 1 million volts or 5 million volts. It's not possible. If you think by 220 kV power system, which is very, very common these days, the test volts are of the order of 1 million volts or more. So if you think of one capacitor here having 1 million volts here, it's not practical. Therefore, what is done is this is split into many capacitors in series and then discharged through these capacitors to get the required wave shapes. Just show the principle. This is known as the Marx generator. So you'll see that the capacitor C1 has got many components, 1, 2, 3, 4 in this figure. Now, these resistors are used for charging of these capacitors. These are all charging resistors. So when you apply a high voltage at this point, this charges up this capacitor. Then through this particular resistance charges this. Through these 2 resistances charges this. Through these 3 resistances charge this. So you will see that if you allow sufficient time, all the capacitors get charged to a certain voltage, which we call the stage voltage. Now, all these spheres have got certain gaps. These gaps are so set as not to flash over unless we want it. The gaps are adjusted so vertically above each other. They are initially set so that they don't flash over. So when we want to get the output voltage wave, what we do is apply what's called a trigger pulse to the first sphere gap here that causes this spark over gap to spark over. That means these two stages get connected in series. This causes this flash over the third stage sphere gap, and then see this capacitor gets added in series. That causes this gaps to spark over, and this also gets added in series. So you see that all these four capacitors get added in series. That means all the four voltages get added. Now that will make this gap flash over. So this capacitor discharges through this resistance, charges up this capacitor. This is a low value capacitance that decides the front time. Once this is charged fully, this capacitance and this capacitors discharge together through this and this resistors. That sets the time to fail. So this is the very basic principle of the mass generator, but expressed in a few words. I hope it gives you a reasonable idea. What we do is we have got multiple stages. Each stage charged to, if there are n stages, each stage charged to 1/n of the voltage, and when they are connected together by a triggering gap, you will see that they get added up to n times the stage voltage. That's how we get very high voltages. Typically, the highest stage voltage is 200 kV. So if there are 10 stages, you get 2 million volts, 200 into 10, 2000 kV. We have got 100 stages, we can get much higher, but they're not very practical. So this is the basic principle of the mass generator. Current generator, equivalent circuit. Oh, sorry. I must say one thing more here. I said triggering of this. How do we do that? This is the first stage sphere gap. You'll see that this one sphere at the high voltage end is another sphere. What we do is this sphere has got a needle at the center isolated from the body, isolated from the spherical body. When we want to trigger the generator, we apply a pulse this needle that causes a spark between the needle and the sphere. This ionization causes spark out of this main gap. Now this is very similar in principle to the ESA arrestor. So in the ESA arrestor, they have got a spark like this, ionization device that causes a flash over this gap. Now, I told you that the stage voltage is typically 200 kV maximum. We have seen that when we don't want spark over, that means we don't want it to fire at this moment, we keep the gap to a high level. For example, 10 centimeters. 200 kV divided by 10 centimeters is only 20 kV per centimeter. It will not cause flashover. But when you want flashover, we give a pulse here that may cause flashover. Now, supposing I increase the 10 to 12 centimeters, it will not cause flashover at all. Even if you apply 100 times, it will not flashover. So you see that ESA rods and this function in a similar way, but the application is very, very different. Here there is a charge capacitor. There you have got a cloud. Here there's a ground electrode and a needle electrode. They have got the ESC rod. But again, if you increase the spacing slightly, even though the field is constant, 200 kV is still there all the time. Whatever spark you apply here, it will not cause flash over here. So we'll see that ESC rod has got its limitations, which is proved by this very, very simple device, which is used day in and day out in high voltage laboratories all over the world. All over the world. This is known as a triggertron gap. Now, impulse current generation, and the time is, how is the time? After deciding on the impulse current generation, we'll go ahead. Now, impulse current generation is much simpler. What we do is we charge a number of capacitors in parallel and then discharge that through an inductance on the test object. Now, the time to front and tail are decided by the object that we are testing. So this discharge through inductance on the test object. So the wave shape of the current is determined by the value of this capacitance and this inductance of the test object also. This is a measuring resistance. So here I got n capacitors equal generator capacitance C1 plus C2 plus Cn. It comes to totally Cg, and then inductance decides the current wave shape together with capacitance. So now this current is applied to the object under test. Most commonly in outside laboratories, lightning arresters or surge arresters used in power transmitters are tested. But when we think of lightning, we can think of either the AC rod or an object like the aircraft. Testing of the AC rod, we have already discussed what are the probabilities under impulses, the probability distribution curves, all those we have discussed, they can be studied. When you think of aircrafts, aircrafts are flying in the high skies also. So, and they are subject to full threat. There's no such limiting of the voltage or current for the aircrafts. So, this wave shape specified is probably the worst case lightning current wave shape. It consists of really typically 4 components: A, B, C, and D. Today I'm having a very severe attack of colds. You must really pardon me. Now this represents the first return stroke. Maximum is 200 kiloamperes. Then the current does not die down immediately. It goes down very, very slowly like that. I'm very sorry. And then there's the second stroke. So this full stroke is considered for the aircraft. Now, since it's not possible to generate this wave shape, which is not properly definable, it has been divided into 4 components. The first component is A, 200 amperes. Please permit me for a minute's break. So you'll see that this current is 200 kiloamperes. That's the worst possible lightning stroke. This is what's called the follow-up current. This is only 2 kiloamperes. Please remember, this is a logarithmic scale. This is 200 amperes, 200 kiloamperes for scale. This is only 2 kiloamperes lasting for 5 milliseconds. That means 5,000 microseconds. Please see, in the time scale is also logarithmic. So this is only about 500 microseconds, not more than that. This is 5,000 microseconds. And then we have got the 200 amperes for a full 1 second. Now, for the first one, it is 200 kiloamperes. Wave shape must not go beyond 500 microseconds. The second one is 5 milliseconds, 5,000 microseconds. The charge is 10 coulombs. For C, the charge limit is 200 kiloamperes. Then charge D, current wave shape D, 100 kiloamperes. That's typically the subsequent strokes, they reduce in magnitude by a factor of half, 200, 150 like that. But the damage is mainly due to A, B, C, and D components. Therefore, that's where the definition ends. So the impulse current generator, as I told you, a capacitor bank discharging through the test object, inductance, and test object. That's what it is. Same thing. What we have got in the lightning test facility, which has been specifically built for testing of light combat aircraft. We have got capacity of 200 kiloamperes, but we have generated even up to 300 kiloamperes. The specifications say that 200 kiloamperes plus minus 10%. The action integral is known as the integral of I squared dt. Remember, for a non-uniform current wave shape, I squared R is the instantaneous power. So the energy loss is I squared R dt in a small interval dt. So the total energy is I squared R dt, integral of that for the entire time. So since we cannot define R in the test object always, the action integral, that's the integral I squared dt is defined. That is in this case 2 times 10 to the 6 ampere square second. Duration must be less than 0.8 microseconds. What we have got is approximately here, approximately 180 microfarads. The inductance of the setup is less than 1 microhenry in our setup. This is a test object, typically in aircraft part. This shows a real wave shape. Magnitude is 200 kiloamperes. This is a real oscillograph only. This from the oscilloscope, this from the plotter. This time is less than 400 microseconds. Action integral is 2 × 10⁶. It has been verified. So the current component B, maximum current transformer is charge transfer is 10 coulombs plus minus 10%. Current is 2 Ka, duration less than 5 milliseconds. Battery bank is a considered option. I've seen it in University of Hanover. They had a battery bank to generate this wave shape, but it's not very easy to maintain a huge lot of batteries. Therefore, what we did was what we considered an artificial transmission line, which consists of a ladder network of C and L like this. We can generate a rectangular wave of this. This is a real wave shape that we have obtained, which meets all the requirements as per standards. Here in our case, we have got each capacitance is 135 microfarads, 2 of them in parallel, that's 270 microfarads. This inductance of the order of 270 microhenries is a surge impedance of 1 ohm. So if we charge it to 4 kV, we get output current about 2 kiloamperes. This is the component C. We have used a power supply itself and a rectifier unit, 3-phase AC, 3-phase, 6-phase transformer. Then a 6-phase transformer using a 6-phase rectifier correction and a filter, we get the output through the component of the AC aircraft under test. This is the actual current we have recorded, which has been passed through the aircraft component. So now current generator D is very similar to current generator A, but the specifications are somewhat different. So here we have got typically 1.5 microfarad, 48 capacitors in parallel. This is the oscillogram. This is also the plotted wave shape. Current is 100 kiloamperes. The duration is such that the action integral is 2.25 10⁶ amperes per second. So now this shows the building. This is adjacent to the old airport, HAL airport. This is the test facility building, lightning test facility. This is the Center for Airborne Systems. It's situated adjacent to the runway. This is the entry from the runway, and runway is below here. So to allow the aircraft, when necessary, to undergo the test, to run into this very easily. That's why it is situated at that particular point. Now this is the Mars generator. It has got 20 stages, 2 microfarads each, 200 kV each. So totally 4 megavolts is the nominal voltage. So this is the current generator. All the capacitors are stacked inside. We cannot keep it open because of the safety issues considered. And then we have got this voltage divider like this. This is a radome. That means the nosecone of the aircraft under test. This is what we call the explosive atmospheric test facility. After about a minute, I will come back to that. So this is a aircraft component under test here. You can see the flashover from the rod to this aircraft. But sorry, this is a not LCA, but a different aircraft. They wanted to give it protection, so they have given the rod here, and then the spark over. Even if it's at an angle, it will not come and hit here. It has come and hit there. We have tried it at many different locations like this by moving the rod here or the aircraft itself, and then we find that all the time it hits either here or here, the wing tip or the most common point is the nose tip, then the fin tip, and then here this avoids all this. There's the pilot's place that's to be protected particularly. So this shows again the aircraft under test, impulse voltage generator here. So this is the aircraft model under test for light, the attachment test. From here we apply a particular voltage and see where it attaches to the aircraft. This is a scaled down model, whether it attaches only to the nose tip or to the wing tip. Is the pilot safe in his cockpit? That's the most important point. Wing tip is here. We have done all the tests and seen that the cockpit is very, very safe. And then attachment is only to the nose tip, nose cone tip, or this. Now, since 70% of the lightning strokes in the field are known to occur by experience, the nose cone. So we do specific tests on that. So this is the Radomer Nosecone. We protect it by 3 strips on the surface. We cannot have a metal radome because inside there is a antenna that communicates with the ground. That without that it's a blind aircraft. We cannot use it at all. Therefore, to protect that, we have got mainly an insulating radome, and then on top of that, protective rods, strips. 3 or maximum 4 located at some distances to test whether its protection is adequate. We apply impulses. You will see that a single flashover has created several paths. It has attached to this strip and also to the other strip there. One more strip here. You will see beautifully the whole thing in this particular photograph. It has branched into 2. A single shot has branched into 2, attached to 2 strips here. And you see the flashover of the gaps in the impulse generator here. It's a beautiful photograph. Impulse generator, the sphere gaps are all located inside. There you can see the flashover there. So now, wingtip. Since wingtip is commonly hit, we provide protection for the aircraft electronics. If the lightning hits here, the current enters the bulkhead and then flows to the aircraft body. It should not create any nuisance for the aircraft. This is the wingtip. Therefore, provision, there's a strip here usually. It comes down and attaches itself to a safe path. The main protection procedure for the aircraft is that provide a comfortable path and it exits. That's all. You cannot avoid lightning under any circumstances. Please note, under any circumstances, you cannot avoid lightning. That's a very important point to note. So again, the radome protection is here. I'm sorry. This is a fuel tank which needs protection, which is under the wing. This is what I told you about. This is what we call the explosive atmosphere test facility. It's a very unique facility in the whole world. Please underline this. The whole world, this is a very unique facility. They've got similar, much smaller facilities, but for this size, it's the only facility in the whole world. You'll see that this is a FRP chamber of required dimensions. We use FRP tube because we are going to fill it up with air at higher temperature of the order of 60 degrees to 75 degrees. That will be the temperature of the air. Since we have to maintain the temperature within plus minus 5 degrees of 70 degrees, we have to have an insulating chamber. Now this is one side wing of the aircraft, LCA completely. One side wing, left. They call it half wing. The full wing is comprising of both left and right wings in the aircraft terminology. Therefore, this is only a half wing. Full half wing is located inside. Then the whole chamber is filled up with hot air, 70 degrees plus minus 5 degrees. The wing is filled up with with fuel vapor. Please remember, the outside, that means in the chamber, we have got air at 70 degrees plus minus 5 degrees. The wing itself is what's called a wet wing. That means the fuel, petrol equivalent of petrol is directly stored in the wing. There's no separate chamber. In all civilian aircraft, the petrol chambers are separate. Fuel wings are separate. Fuel storage has got a separate box. Here, the wing itself is stored in direct contact with the fuel all the time. The reason is they want to save weight. They want to save weight. So now this wing is filled up with fuel vapor. In fact, we use a vapor of acetylene and something so that it's far more ignitable than the air fuel. Therefore, we close it. The chamber top is here. We close it. Then fill it up with hot air, fill it up with fuel, and then apply full thread lighting impulses to the selected points, the wing tip, and these edges we apply the pulses. We have supplied it. I'm extremely happy to tell you that the production scheme worked out has passed dramatically well, absolutely no failure at all. Similarly, the fuel tank, which is underneath the wing, is hanging outside, so that once what they do is they first use the fuel in this wing tank under the wing, which is hanging under the wing. Once this is used up, this is dropped off, so that you gain weight. That we gain weight loss is weight gain for the aircraft, so that it can, for the same amount of fuel, it can fly for longer distances. So this the wing tank is placed inside the special chamber, then filled up with fuel, and the chamber has got fuel, rather hot air at 70 degrees plus minus 5 degrees, and then it is subjected to full threat lighting strokes. There should be no ignition at all. If the ignition is there, it has been seen only once due to some error in the setup. It was really colossal. It was worse than any lighting we have seen in real life. So such tests are known as explosive atmosphere tests. Explosive because there's an explosive mixture inside and then hot air outside to represent the worst conditions in real life. So thank you very much for listening to this rather long lecture. I must really apologize for extending the time beyond the limits. I must thank Mr. Gopakumar and every one of you once again for the patient hearing, and I hand you over to Mr. Gopakumar and then the question session if it is permissible.
Thank you very much, sir. It was quite interesting lecture.
Thank you.
Yeah. So and all the almost all the technical details are discussed and explained. This will be very much helpful for the engineers, those who really wanted to do study on lightning. We will be publishing this video, will be put on the website vidyutsuraksha.com in the blog probably after half an hour after finishing this program. So you can also look into it. We have few questions, very few questions. I will just read it, sir. The first question is from Mr. James Kuti Thomas. In fact, Mr. James Kuti Thomas is a retired electrical inspector from Kerala State Electricity Electrical Inspectorate. He is also an advisor of our Vidyut Suraksha Bharat Abhiyan program. He is supporting us very much. And he is also an expert in lightning protection of buildings. So the question is about, sir, it is clear that the most selling air terminals in India is ESC. What you understand the trend behind? Why can't government take any legal steps against them, being a violation of our rules and causing many accidents?
What you say is perfectly right, because use of ESC rods, if it is as per IEC norms, same as per normal Franklin rods, there will be no questions. But my feeling is that they have not followed that. Since they have not followed it, it's certainly a gross violation of the national standards, international standards, I should say also. I do not know why they have not taken action. It must be probably the influence of the ESC manufacturers or whatever it is. I'm only guessing. I may be wrong, whatever it is. I also hear, I don't know whether I'm right or wrong, that there have been many failures, but none of them have been reported to my knowledge. It is this lack of reporting of the failures that has led to this type of situation. I don't know. I don't know what I should do really in this connection. I feel only sad, very sad in our country. As I told you, in Malaysia, they have banned it because they have seen the failures. They have been reported and the government has recognized that they have been failing. Here also, unless the failures are reported, what can the government do? The failures must be honestly reported. That's where the real fallacy lies. If they are not reported, they must be hiding because they don't want to accept it. That's the tragedy of it. I don't know. This does not answer your question. I'm 100% sure. I don't know what more to say. People who use it, they're welcome to use it. But if there's a failure, they must report it immediately. I think if that is done, things will automatically fall into groove and things will be right. I don't know what you say, Mr. Gopakumar.
Yeah, sir, there are several incidents. Say, for example, in 2012, the Hindu newspaper has written that Madurai Meenakshi Amman temple, one of the oldest temple in Tamil Nadu, they have installed 7 ESC rods and the entire area is protected. This was the paper news. But in 2013, the same newspaper had made another news saying that the lightning has struck one of the gopurams and it was damaged.
My God.
So similarly, yes, it is a failure. But and there is a report also from the Electrical Inspectorate of Tamil Nadu explaining that these ESCs will not work. It is the building is the temple is not protected. In fact, then similarly another case, Puri Jagannath temple. It was actually not a good story from a multinational company, Mrs. ABB. ABB has bought a company a few years back called as an ESC company from France, and they were selling ESC in our part of the world. I don't think that they will be able to sell it in Europe or Americas. However, the corporate news article, their corporate news, they have claimed that from Zurich, they claimed that all the temples and monuments of Orissa has been protected by ABB early streamer emission rods. This happened in 2016. I think 2016 or 17. But after 2 years, the Puri Jagannath temple was hit by a lightning and it was very big damage. I think ABB immediately took back this message. They have removed it, I hope. So like that, a lot of accidents are happening. Yes, sir. Yes, sir. But the only thing is we are not following it up properly.
Yeah, you see, there needs to be, I think, proper documentation of these failures without any hesitation, and on part of the manufacturers, and they must be very, very honest to themselves. They must be very. This is the only thing that's needed really. If they are honest to themselves, the manufacturers, they must accept the failures of their own devices. They must withdraw it from the market once and for all. They must close down the manufacturer. What else can we do as civilians? What is it that we can do? All the failures, all the people must go and appeal to the proper authority. For example, disaster management authority or whatever. I'm not very sure what it is. I think, and give it very wide publicity so that there's a hullabaloo about that. That's the only way. What else can you do in a democracy? What else? I really see it's a very dark question, a very, very dark question. Question is there, not seen at the right in the right quarters.
Yeah. The next question is what is this radioactive air terminal dissipation system and controlled CSE system, controlled streamer emission?
You see, as I explained to you in my webinar itself, they're all differently worded. They're all differently worded, but basic claim is that there is a pre-ionization scheme which causes the streamers to develop much earlier and go and meet the leader before a Franklin rod does it. That's the only claim, really. Basically, that's the only one, which is very, very wrong, only differently worded. As usual, the typical mentality in India is that anything made abroad is better than made in India. If they have got foreign collaboration, foreign names, they accept it more than the local ones. That's all. The cheaper one, that's more costly, it must be better. That's a simple logic. Costlier one must be better. In fact, I have seen in the internet itself, one particularly ESC terminal costs 90,000 rupees. I do not know. It is mind-boggling. 90,000 rupees for one terminal. Claims to protect so much area, but does not. Because all of them are banking on the fact that lightning incidence is highly probabilistic. If it strikes in one point this year, it may not strike at all for next several years. That's the probabilistic nature of lightning, which is really supporting the claims of these people. Nothing else about that, because it's highly probabilistic.
Yes. Yeah. Thank you very much, sir. We have Mr. Davis had raised the hand. Mr. Davis, you can unmute yourself and ask the question.
Yeah, Mr. Gopkumar, and thank you, Professor. It was a great session. I was refraining from making any questions here, because the way you explained technically all the myths, you busted all the myths, I would say, on lightning. I only have a guilty feeling. I have, at least in my 35 years, I would have corrected many ESEs, at least 35 numbers in major buildings. So, and of course, I was not convinced about it, but then that was need of the hour, or the customer was paying for it, and we have been doing. But I have ensured the down conductors are properly done. So, thank you, sir. Thank you very much for this. I think I would say the way you explain the myths busted through a lightning stroke of technical capabilities. Thank you, sir. Thank you very much.
Thank you. Thank you. I must thank you for your great interest and honest opinion.
This is only way
Thank
to
you, Mr.
break this
Davis.
myths. This is only way to break the myths. Thank you, sir.
There's no other way.
Thank you.
There's no
Thank
other
you.
way.
The next questions are from Mr. Madhav. We see many farmers construct a tin shed in their farms being used for cattle and also for storing farm produce. The support structure of such tin shed is mostly GI angles and pipe. How safe or unsafe these sheds are against lightning?
They can be made very safe by providing appropriate rods and grounding them very properly, and most probably with a ring earth all around. I think that's the best way of definitely protecting not only cattle but also humans. It my zinc shed. The only problem is if the zinc sheet all around, current density does become very small, and then the safe distance must be, if nobody should touch it from less than about 1 meter, and then a ring earth which is about 1 meter deep should be really very good. Should be really very good. That's the correct answer for open area protection. That's
Yes,
my
actually, when we talk about this cattle shed, there the 2011 National Electrical Code, I don't remember the exact number of the session. With pictures, the measures are given, but unfortunately, only these professionally managed cattle farms are going or doing these kind of safety measures. But the normal farmers are not very much keen on that because there is no finance, there is no funding, or there is no money available.
There's no finance.
Thanks for the question, sir.
Yeah.
Yeah. Sir, we have Mr. James Kutty Thomas. Mr. James Kutty Thomas, you can unmute yourself and have a word with Professor. You have written a lot of questions, so you can also ask directly. So there is a question from Mr. James Kutty whether we can have a visit to the lab.
You want light test facility?
Yes.
A visit to that should be possible. The only thing is right now there is some construction modifications are going on. I don't know how long it will take, maybe a couple of months. The best person to approach for you is Dr. Pradeep Kumar Dikshit, our colleague in these lectures, these webinars. He is having a project, but at the moment, it may not be possible in the immediate moment. But there are two things. Now, I started constructing this in 1989. 92, it became functional. But till I retired, I was in charge of the whole laboratory, including, in a way, indirect way, the security also. I was allowing to take anybody in and out, no problem. Till about 2018 almost. But subsequently, it has been handed over to CAPS. It was originally property. The laboratory was property of Aeronautical Development Agency, who funded the laboratory. But right now, it has been transferred to Center for Airborne Systems, in whose area it exists, adjacent to the airport. Therefore, it needs the permission of the director of CAPS, the Center for Airborne Systems, and at the moment the functionality of the laboratory. As I told you, it became functional in 1992. So now we have been maintaining it through projects. It has been, even a few months ago, it has been functional, but I don't know the exact situation now because there has been some constructional changes in the laboratory building. Only Professor Dikshit would be able to give you the correct answer situation there now.
Yeah, Professor Dikshit, you can also unmute yourself, and if you wanted to add any answers, you can also add, please. Also, sir, there are a lot of messages regarding the knowledge which you have shared, and a lot of thanks for you. Also, Mr. James Kutty also told that why don't you make this as a book, or if there is a book already available, please inform. Any books available, sir?
No, to my knowledge, says exclusively content of this much only. to my knowledge. But very detailed information about lightning and lightning phenomena, etc. Definitely there are many available. In fact, including Vernon Coure's book, and then Martin Newman and Rakoff, they have then written extremely exhaustive books. But the specific discussion on ESC, to my knowledge, is not there in anyone. Because it is not of general interest in the sense, though there's a commercial issue, legal issue. I don't think there's any article on that. I don't know. If you think, as you said, if you have since you have made it public on the webinar, I think that's the best thing that you can do. Huh?
Yes,
To my
yes.
knowledge,
Thank you,
there's no
sir.
book.
Gopakumar, good afternoon, Dixit here.
Sir, tell me, sir.
Yeah, whatever James Kuti was asking, as Professor mentioned, you have my number. You can give it to James Kuti. At any time, he can call me. I will try to arrange, as the Professor told. Now, the small constructions are going on in the caps. I'll talk to the director or the in charge of the LTF. Then I'll come back for the visit. I can arrange for the visit.
Thank you very much, sir. Thank you very much. Mr. James Kuti,
Okay,
sir,
okay,
I will
thank you,
give the
sir.
number. I will give the number. You have any questions, Mr. James Kuti?
No. Okay, thank you, sir. Thank you, Pradeep Kumar, sir, and doctor. It is actually the contents of the video class was a little bit advanced, but we will go through the video more and more, and we will study in deep. And thank you for your continued support.
Yes, thank you.
There is one possibility. I don't know how people like it. If you can talk to the director, those who are interested, if they can form a group and contact the director of CAPS, and of course with Pradeep Kumar Dikshit in this connection, maybe these ESC rods and Franklin rods may be compared under lighting pulse voltages for their performance for various wave shapes also. But that will be fairly good work. It will be somewhat time consuming. It will also be money consuming because the caps, they charge us some money per day basis. It may take a fairly long time. It may involve quite substantial money. But if any of you can talk to the director of caps also, he may be willing to give it free because it's a matter of national importance. But I cannot really make any specific statement on that more than this.
Yeah, sir. Thank you very much, sir. Also, Mr. James Kuti told that in Kerala last 2-3 months there were several incidents, including some police signaling system because of ESC. So we have Dr. Rajesh he has raised the hand. Dr. Rajesh, you can unmute yourself and ask the question, please.
First of all, thank you, Gopal sir, and thank you, Professor Saab. I have attended so many webinars on lightning. This is one of the best I attended, and fortunately, I could attend all the 4. And my queries are related to your table. In table you have shown when the lightning happens, there is some step potential and some touch potential, and you are mentioning that table that for the worst condition, the 30 amperes will flow, and in the safer side, that is 300 milliampere will flow to the body of that human that may touch. But again, I feel that is on the very higher side. But no recommendation from your side was given to take care of that high current that is actually harmful for the human being who is going to touch that tower at the time of light. Kindly elaborate that point.
Can you kindly repeat the question? I did not understand it fully.
Yeah, actually, in one of table you have shown that when the lightning strike any transmission line tower, the maximum current or minimum current that may flow is 300 milliampere and 13 ampere. Okay.
Yeah.
If that is on the very higher side, so for the safety of a person is concerned, what are the methods to be applied to mitigate that thing? Kindly elaborate on that thing.
You see, there are 2 issues here. In those calculations, there have been certain assumptions which are very clearly specified also. The body resistance has been made 0. That's point
Yeah,
one.
that is a
Second,
case of wet condition. You are right. No
correct.
problem.
Correct. The second point is that what the criticality of the current magnitude to a person, lady or child or a patient or a man. Now that cannot be determined, as I mentioned to you during the webinar also, because there's an experiment which may result in fatality or a serious lifelong injury. That will be an experiment which is impossible to take up. Therefore, it's very difficult to state what current is tolerated, what current is not. For example, even under AC conditions, we know that we have got let go currents. If the current is less than about 7 to 8 milliamperes, the man can get low, can let go of the current conductor. If the current is more than about 15 milliamperes, if a man is holding that conductor, he cannot even let it go. 15 milliamperes. Here,
I
they're all.
understand. That's why I asked that question.
No, correct. Even there, even under AC conditions, experiments beyond that, in principle, simply not acceptable because we'll be possibly endangering the persons to a very serious extent. That's the problem. It's a problem with all electrical conditions, and impulse is certainly not think of not acceptable current at all.
But my concern is that why the authority in India have given the recommendation of 10 ohm resistance value for all transmission line in India as per IS 5613. What was the logic behind?
You see, there are several things here. This 10 ohms is the earthing resistance of the whole rod of the system as a whole. Now, this is measured with a DC meter at a very low current, maybe a few amperes.
Right.
These standard DC test kits. Now, the second thing is this is under DC. Under impulse conditions, the soil resistance varies. But the exact variation depends upon the soil composition, the dryness, moisture content, etc. Exact variation is not clear because the soil condition is very different from place to place. Even in one place, it can vary. That's point one. Point two, it varies with the current. The impulse current, it varies with the impulse current. If the soil is very conducting, for example, if you think of garden soil or alluvial clay, I have mentioned it in the earlier table, the estimate is of the order of 1 to 10 ohm meter. Then under impulse conditions, it will not change substantially. Whereas, if you think of the higher resistivity soils, for example, say 100 ohm meters, it may come down to 40, 50 ohm per meter. So therefore, you will see that the so-called earthing resistance of 10 ohms, with all the conditions, that's considered safe because that's under DC conditions with a low current. When we go to higher currents, under impulse conditions, the resistance will come down substantially, I think. I have not made any measurements in that. I don't have any data also on that. I must confess that much. Except stating these some background facts, I don't have anything else to suffer, I must say.
And sir, if you allow, I would like to talk on that topic in depth. If you allow me, I will call you later on.
Sure. Whatever I can, I'll be of some help to you. Whatever help
I would like to share the data I have with me related to that problem. I would like to share with you.
Wonderful. I'll be happy.
Okay, thank you. Thanks once again for that mind-blowing session, should I say.
Thank you very much. So kind of you.
Okay.
Thank you. Thanks to all. Thanks, Dr. R Nagabhushana sir, for making this program highly successful. We had 100 plus participants even today. Now we have about 57 at the moment. So all the 4 programs were successful. So because of you, and we have a lot of the YouTube videos which we have put, there were more than 1,000, I think 1,200 people viewed the videos. So that means the subject which we discussed is getting popular. Thank you very much for that, sir.
I'm really surprised.
Also,
And I must thank you for this opportunity. Otherwise, I would have kept quiet. That's all to myself. Nothing more, nothing less. I must thank you profusely for this great opportunity and this situation of happy sharing of the knowledge, whatever it is. I'm very, very happy about that part. Thank you very much for that.
yeah, thanks, sir. Also, thanks to Professor Pradeep Kumar Dikshit for all the supports. he was supporting us behind the curtain, preparing all the presentations and so on. Thank you very much, Professor Pradeep Kumar, sir.
Thank you, sir. Thank you. It is our pleasure.
And yes, and finally, all the participants, thanks to all the participants, we had Mr. Bhavani Prasad in between. I think yesterday and today also he was there, but he has put some comments as well today. But Mr. Bhavani Prasad is the classmate of Nagabhushana sir, the retired,
Right.
yes, Director General from CPWD. So anyway, he is not available in the group at the moment. He has discontinued. So thank you very much, all of you. Thank you very much, sir, especially for making this program successful.
Thank you
So
very
by
much.
this, we will.
It has been, you have given me this privilege. I must thank you and every one of the participants. I'm very grateful for this occasion. Thank you. Thank you.